4 bearing types, 1 shared idea. Take something round, a ball, a roller, a cone, a needle, and let it roll between 2 surfaces. That single idea carries an enormous share of the rotating machinery on Earth, but it has limits. It assumes the load pushes sideways against the shaft. It assumes there's room for a raceway. It assumes rolling contact is even possible in the first place. Sometimes none of that is true, so engineers need a different idea entirely. This is part 2 of bearing types every engineer should know. Last time we covered ball, roller, tapered, and needle bearings. 4 designs that all solve their problem through rolling contact. This time, the rules change. Let's pick up where we left off. Every bearing so far has answered the same question. How do you support a rotating shaft against forces pushing sideways? But what if the force doesn't act sideways anymore? What if it tries to push the shaft straight through the machine? Imagine the propeller shaft of a cargo ship. Every rotation pushes thousands of kilograms of water backward. Newton's third law pushes the entire shaft forward with exactly the same force. Or consider a vertical hydroelectric turbine. The rotor itself may weigh several hundred tons. None of that load acts radially. It acts directly along the shaft. A radial bearing can survive small axial forces. It cannot survive becoming the primary load path. Engineers needed an entirely different answer. Instead of surrounding the shaft with rolling elements, they positioned the rolling elements between 2 opposing bearing washers. The load no longer passes through the circumference of the bearing. It passes directly across its faces. This seemingly simple change redirects the entire force path through the machine. The challenge now becomes uniform load distribution. Every rolling element must share the axial load almost equally. If one ball or roller carries significantly more force than the others, fatigue no longer develops gradually across the bearing. It begins locally, and local failures rarely stay local for long. Speed introduces another complication. At high rotational speeds, centrifugal forces try to move the rolling elements outward, while lubricant is simultaneously forced away from the loaded contact surfaces. Maintaining a stable lubricant film becomes increasingly difficult. That's why high-speed thrust bearings often rely on continuously circulating oil systems rather than grease. The lubricant isn't simply reducing friction anymore. It's cooling the bearing, transporting contaminants away from the contact surfaces, and maintaining the fluid film that prevents metal-to-metal contact. Whenever the dominant engineering problem becomes axial force instead of radial force, thrust bearings become the correct answer. But they also reveal something important. Not every engineering problem requires inventing a completely new machine. Sometimes it only requires changing how the forces flow through it. At this point, it might seem like rolling elements are the obvious answer to every bearing problem. After all, every new bearing we've discussed still uses balls or rollers. So why would any engineer deliberately go back to sliding friction? The answer is surprisingly simple. Because sometimes the rolling elements become the problem. Consider the turbine shaft inside a power station. It may rotate continuously for years while supporting enormous loads. The bearing itself can measure over a meter in diameter. Building a rolling bearing that size would be extraordinarily expensive. Keeping it lubricated would be even more difficult. Instead, engineers often remove the rolling elements entirely. A plain bearing consists of little more than a precisely machined sleeve surrounding the shaft. At first glance, it appears to be the simplest bearing imaginable. In reality, it's governed by some of the most sophisticated fluid mechanics in mechanical engineering. Here's the remarkable part. Once the shaft reaches operating speed, it stops touching the bearing altogether. As the shaft rotates, it drags lubricant into the narrowing gap between the shaft and the bearing surface. That narrowing geometry creates pressure inside the oil itself. The pressure rises until it becomes large enough to lift the shaft completely off the bearing surface. The shaft is no longer sliding, it's surfing. Only a microscopic wedge of oil, often thinner than a human hair, supports the entire rotating assembly. The engineering challenge has completely changed. Engineers are no longer designing contact mechanics. They're designing fluid flow, clearance, oil viscosity, surface finish, temperature, rotational speed. Every one of these determines whether the oil film remains stable. If that film collapses, even briefly, direct metal contact occurs. Wear accelerates almost instantly. But when the hydrodynamic film remains intact, the bearing offers extraordinary advantages: extremely high load capacity, outstanding vibration damping, exceptional durability. This is why massive steam turbines, hydroelectric generators, marine diesel engines, and compressor shafts still rely on plain bearings. Sometimes the oldest idea remains the best one, not because it's simpler, but because physics makes it superior. Yet even oil eventually reaches its limits. What if lubricant itself becomes the problem? In semiconductor manufacturing, optical inspection systems, and ultra-precision machine tools, even microscopic vibration can ruin the final product. Oil introduces viscous drag. It changes viscosity with temperature. It can contaminate precision components. Engineers needed another answer. What if the shaft floated on air instead? Air bearings replace liquid lubricant with a continuously supplied cushion of pressurized air. Tiny restrictors distribute air evenly beneath the rotating surface, creating an incredibly thin but remarkably stable pressure film. The shaft never touches the bearing. There are no rolling elements, no sliding surfaces, virtually no wear. Friction becomes almost negligible. Without mechanical contact, vibration falls dramatically. Positioning accuracy reaches nanometer scales. This is why air bearings appear in coordinate measuring machines, wafer fabrication equipment, optical stages, and ultra-precision grinding machines. But this solution comes with perhaps the greatest trade-off we've seen so far. Air is a terrible structural material. Its viscosity is roughly 2 to 3 orders of magnitude lower than that of the lubricating oil used in a conventional bearing. Generating sufficient pressure requires extraordinary manufacturing precision. The air film itself is only a few micrometers thick. A small contaminant particle, a slight interruption in air supply, a manufacturing defect almost too small to measure. Any of these can collapse the air film. Unlike a ball bearing, which tolerates temporary abuse surprisingly well, an air bearing depends on maintaining an invisible structure made entirely of flowing gas. The shaft isn't supported by a solid component anymore, but by carefully controlled pressure. And that naturally leads to one final question. What if you removed the air cushion too? What if the shaft never touched anything at all? Some of the fastest rotating machines on Earth operate exactly this way. Inside high-speed compressors, turboexpanders, flywheel energy storage systems, and vacuum pumps, the shaft doesn't ride on balls. It doesn't ride on rollers. It doesn't ride on oil. It doesn't even ride on air. It floats. Electromagnets surrounding the shaft continuously pull it toward the center of the bearing. Position sensors measure the shaft's location thousands of times every second. Control electronics instantly adjust the magnetic forces to keep the rotor perfectly centered. No physical contact exists during normal operation. No lubrication, no rolling fatigue, no mechanical wear. The rotor can safely operate at rotational speeds that would rapidly destroy conventional bearings. It sounds like the perfect solution, but once again, engineering refuses to give anything away for free. Every bearing we've covered so far, across both videos, solved its problem through geometry, or through a fluid film shaped by that geometry. The shape of the rolling elements determined how forces entered the machine. Magnetic bearings are fundamentally different. Their geometry alone cannot support the shaft. In fact, permanent magnets by themselves cannot create a stable levitation system. Without continuous electronic correction, the rotor simply crashes into the housing. The bearing only works because sensors, electromagnets, power electronics, and control algorithms operate together as a single system. The bearing has evolved into a computer-controlled machine. Mechanical engineering alone is no longer enough. Electrical engineering, electromagnetics, control theory, software, all have become part of the bearing itself. It's the logical endpoint of the question we began with 2 videos ago. How do you support a rotating shaft? Sometimes you don't support it mechanically at all. 8 bearings, 1 question, asked again and again under harder conditions. Support the shaft with point contact and you maximize speed. Spread the load into line contact and you increase load capacity. Shape the rollers into cones and you handle forces from multiple directions. Make them thinner and you solve packaging constraints. Redirect the load path and axial forces become manageable. Replace contact with fluid pressure and vibration disappears. Replace oil with air and precision reaches the nanometer scale. Replace contact altogether and the bearing becomes an active control system. Notice how the engineering evolved across both videos. It didn't move from simple to complex, it moved from solving one limitation to solving the next. Every new bearing exists because the previous one eventually encountered a constraint it could no longer overcome. That's how engineering progresses, by asking the same question again under more demanding conditions. If you want to understand machines at that level, this is Engineering Manual.